Hey guys, today I'm going to walk you through my model of working memory here at aithought.com. And the title here is Thought is Structured by the Iterative Updating of Working Memory. Implementing this in a machine could enable artificial general intelligence. And today I'm going to focus on the figures and explaining what the figures mean. So here we have four different moving figures. They're animated. And in the first one on the top left, it shows the iterative updating of working memory. So my claim here, my major claim, is that consciousness and intelligence are possible because working memory or attention is updated iteratively. So there in that black box, you can see the focus of attention, and that's what you're conscious of. And you can see concepts moving out of the focus and into the short-term memory store. So what's in short-term memory and in the focus of attention work together to select the next iterative update. And you can see these updates are circles with capital letters inside. So each one would be equivalent to a concept or an idea or an item in working memory. So that could be a cookie or a car or a verb like running or a person. And here I'm arguing that the neurons that make up those concepts in the brain all fire together to converge on the next conceptual association in the brain. And that's shown here in this figure here. So here you see there are four main letters that are uppercase, and those shown with a big circle. And then each of those are made up of many different neural assemblies, which themselves are composed of brain cells, neurons. So what's active in your mind involves a number of different concepts that together create a scene or an event, a static image of something going on. And then all of those neurons fire together, sending their spreading activation throughout the brain, converging on another set of neurons, and whatever concept most closely links to that new set of neurons is going to be the new iterative update to your consciousness or your attention or your thought or your working memory. And that's where you go from static events to a narrative, where things move and change through time. And I believe that that's really the basis for reasoning. So here now in the bottom left, you can see that a number of different systems all contribute to the selection of the updates. You can see it's not just one update necessarily, it could be a number of them. Here we added O and N to the focus of attention. And then here on the right, this is labeled information shared between successive states of working memory creates the continuity of consciousness. And this is where I have basically a new theory of consciousness saying that it's really the overlap between individual states that creates this bridge through time that we experience as consciousness. Okay, so let me read the abstract to you quickly. This article provides an analytical framework for how to simulate human-like thought processes within a computer. It describes how attention and memory should be structured, updated, and utilized to search for associative additions to the stream of thought. The focus is on replicating the dynamics of the mammalian working memory system, which features two forms of persistent activity: sustained firing, preserving information on the order of seconds, and synaptic potentiation, preserving information from minutes to hours. The article uses a series of figures to systematically demonstrate how the iterative updating of these working memory stores provides functional organization to behavior, cognition, and awareness. So in a machine learning implementation, These two memory stores should be updated continuously and in an iterative fashion, meaning each state should preserve a proportion of the coactive representations from the state before it. This makes each state a revised iteration of the preceding state and causes successive configurations to overlap and blend with respect to the information they contain. Thus, the set of concepts in working memory will evolve gradually and incrementally over time. Transitions between states happen as persistent activity spreads activation energy throughout the hierarchical network, searching long-term memory for the most appropriate representation to be added to the global workspace. The result is a chain of associatively linked intermediate states capable of advancing toward a solution or goal. Iterative updating is conceptualized here as an information processing strategy, a model of working memory, a theory of consciousness, and an algorithm for designing and programming artificial general intelligence. So I published these in 2022. Here are the articles. These are both are an archive, and this was an article that was peer reviewed in 2016. They all relate to this same model. Now in 2026, instead of talking about AGI, I should probably be talking about superintelligence. Here's the table of contents. And let's really just focus on the figures here. So the general features of this model are that it's connectionist, recurrent, autoregressive. It's constantly processing even in the absence of input or output. And you can read the rest. But this is an overview of the features of the iterative updating model. Okay, here figure 1. Each row contains 5 rectangles labeled time 1 through time 5. Each rectangle corresponds to a state of working memory holding 3 items. In the top row, successive rectangles do not hold any of the same items, indicating complete updating. So there's no iteration here. In the second row, though, 2 items are shared between successive rectangles, indicating partial updating. This article contends that the iterative nature exhibited by the second row is a fundamental attribute of the thinking process. And then here we have a flowchart of iterative updating. In an iterative process, a set of components is modified repetitively to generate a series of updated states. Each state is an iteration as well as the starting point for the next iteration. One way to accomplish iterative modification is to alter a given state by retaining pertinent elements and then subtracting and adding others. In the brain, the content to be added and subtracted is determined by spreading activation. So here we're now entering the literature review, and so the next few figures are not going to be designed by me. So this is Atkinson and Shiffrin's multi-store model. This model depicts environmental stimuli received by the senses and held in sensory memory. If attended to, the stimulus information will enter short-term memory, i.e. working memory shown in gray. If not rehearsed, it will be forgotten. If rehearsed, it will remain in short-term memory, and if sufficiently elaborated upon, it will be stored in long-term memory, shown in black, from which it can be retrieved later. Long-term memory is depicted in black here and throughout the article. And then this is Badley and Hitch's multi-component model. In this model, the short-term store from Atkinson and Shiffrin's model is split into 4 interacting components that together constitute working memory: the visual spatial sketchpad, the phonological buffer, the central executive, and the episodic buffer, which was added later. Okay, and then figure 5 is a prototypical cognitive architecture. So this figure incorporates aspects of various popular cognitive architectures and indicates the neural substrates thought to support these memory functions. You can see that information enters the brain through sensory memory, first through our senses like our eyes and our ears, and then in the parts of the brain that first receive that information. Then it goes to the phonological buffer for sound and language, and the visual spatial sketchpad for visual imagery. Then those things are transferred to working memory, and they interact with episodic memory, declarative memory, and procedural memory. And the goal buffer to determine actions. All right, and then here's Bars and Gage's functional framework. So working memory activates long-term memories, knowledge, and skills, which are shown in the box at the bottom. Spontaneous bottom-up attention and voluntary top-down attention are symbolized here as vectors. All right, and then here's Barr's global workspace model. So the brain has several lower order modules that are generally isolated from each other. And here there are 5 different arrows. Unconscious processes and environmental stimuli processed by these modules compete for access to the global workspace. So you can see that the space allocated to each of these 5 different arrows is bordered by these walls, these lines there. So at first, the long-term memory and the perceptual systems, the motor systems, they can't speak to each other. They're each working on their own independently, on their own inputs and their own processes. But all of that information is sent to an area where there's actually a lot of communication going on called the global workspace. So again, the most salient inputs enter the workspace where they're integrated, stored temporarily, and made conscious. These results are then broadcast back to the rest of the brain. And then here we have Cowan's embedded processes model. So according to this model, short-term storage is an activated subset of long-term storage. Similarly, the focus of attention, or the FOA, is an attended subset of short-term storage. These stores interact with a store for sensory memory and a central executive. So what this means is that what's in your focus of attention is a more active version of what's in your short-term memory. And then that itself is a subset of everything possible held in your long-term memory. And then here is a figure showing different forms of human memory. So human memory can be divided into 3 phases, each of which can be decomposed into other forms. Here you can see that sensory memory at the top left can be divided up into visual and auditory memory, which are very short-lasting. Then working memory lasts less than an hour. The focus of attention generally lasts between 1 and 60 seconds, and the short-term store lasts from minutes to hours. And then we have long-term memory, which can be decomposed into explicit and declarative, and those two can be broken down even further. Okay, so now we have introduced 2 new concepts, and those are 2 of the most important here: sustained firing and synaptic potentiation. So sensory memory, as we can see, is basically possible because of neurons that happen to be firing. The focus of attention happens because of a certain process in the brain called sustained firing that allows a neuron to remain active for several seconds at a time. And then the short-term store, a memory will remain in your short-term store after the neurons responsible have stopped their sustained firing. But because of a chemical trace that lasts for a few hours, that memory is easy to recall, and that's called synaptic potentiation. Then when you remember something long-term that happened days ago or years ago, that's because of physical change in the brain called long-term potentiation. So there we looked at the brain correlates. It might help to study this table for a minute or 2 before we continue. So this table summarizes some of the major comparisons between 4 different forms of memory. The details addressed in this table are not definitive and are active areas of debate and research. Okay, and here we have recurrency and artificial neural networks can simulate persistent neural activity. a simplified version of an artificial neuron used in computer science with inputs and weights labeled. That's there on the left. Now B, an artificial recurrent neuron in a hidden layer passing information from an input layer to an output layer. This hypothetical neuron, inspired by Table 2, exhibits recurrency in its cell body, which is later converted to recurrency in its weights. Thus, it demonstrates an analog of both sustained firing and synaptic potentiation. And then C, on the right, recurrent neuron unfolded through time. The activity of this hidden neuron is unfolded through time as it goes from inactive to partially active. So it's very clear that we can get artificial neurons in computers to show the same kinds of response properties as those in the brain here in this table. And I think that would be important if you're trying to create machine consciousness. Okay, so now we're moving past the literature review into part 3, which is working memory is updated iteratively. So here, the sustained firing of 20 hypothetical neurons is shown. The x-axis represents time. The spans of individual neurons overlap but are staggered and asynchronous. T1 and T2 are marked at the bottom. The two time periods share 10 of 20 active neurons in common. This figure exemplifies the transitional reconfiguration that distinguishes iterative updating. Here's figure 12. It's a depiction of iteration in neurons exhibiting sustained firing. Each arc, designated by a lowercase letter, which means that these are not concepts but neurons that make up concepts, represents the time span during which a neuron exhibiting sustained firing remains active. The x-axis represents time. Dashed arcs represent neurons that have stopped firing, whereas full arcs denote neurons that are still active. The neurons shown here demonstrate iteration and recursion. Okay, and then this is one of my favorite figures here. These are Venn diagrams of information shared between successive states of working memory. So these Venn diagrams depict informational overlap between successive states of working memory. Again, when it's black, that's long-term memory that's not activated. When it's gray, that depicts memories that are held in the short-term store or short-term memory, STM. And when you see white, that is information or memory that's held in the focus of attention. So here the horizontal axis represents time. The small white circles represent information within the FOA, while the large gray circles represent information within the short-term store. Diagrams 1 and 2 show no Venn overlap between states from different periods. 3 and 4 show overlap in the short-term store only. 5 and 6 show the short-term store of one state overlapping with the FOA of the neighboring state. And 7 and 8 show the FOA of separate states overlapping, suggesting attentive continuity. Given the time constraints noted in Table 2, it may be plausible that diagrams 1 and 2 roughly depict sampling of cortical activity hours apart. 3 and 4 depict sampling several minutes apart. 5 and 6 depict sampling every minute, and 7 and 8 depict sampling every second. So I believe that this figure is really a graphical representation of consciousness. Okay, here we're defining the terms that we've introduced so far: iteration, working memory and working memory updating, and iterative updating. And here's figure 14. It's an abstract schematic of iterative updating in the FOA. As with the following figures in this article, figure 14 is an emblematic abstraction that uses a state space model in discrete time. White spheres indicate active mental concepts or items, while black spheres indicate inactive ones. At time 1, item A has just been deactivated, while B, C, D, and E are coactive. This echoes the pattern of activity shown in figure 12, except that the uppercase letters here represent items, whereas the lowercase letters in figure 12 represent neurons. While coactive, these items, B, C, D, and E, spread their activation energy, resulting in the convergence of activity onto a new item, F. At time 2, B has been deactivated, C, D, and E remain active, and F has become active. So, this series illustrates the iterative working memory activity of a person who thinks about watering a plant. The person imagines a wilting plant with dry soil. This set of coactivates in working memory spreads neural activity, which converges on the concept of water. This new set, in turn, induces the ideation of using a watering can. The person then imagines tilting and then pouring the water from the watering can until they stop watering the plant. And I think that this shows how working memory updating can mediate intelligent transitions between mental states. Now, this shows the capacity limit of working memory varies. So, 4 different examples of working memory capacity from 2 to 8. The capacity of working memory can vary from trial to trial, person to person, and presumably from species to species. The idea is that studies show that most people have a working memory capacity of 4 items, but it's more like 7 when you're not correcting for all kind of complicated variables. Okay, so this shows 4 updating replacement schedules. So here the item removed or evicted can be the oldest entry in working memory, which would be first in, first out, the newest entry, which would be last in, first out, or anything in between. The least informative or relevant item should be the one selected for replacement. All right, and then this shows how working memory responds to and navigates interactions with the world. Items marked with an S represent external stimuli, while items marked with a C represent internally selected concepts. This series illustrates the working memory history of a driver responding to a green light that turns yellow. The yellow light in this context prompts the driver to check their distance to the intersection. When they find that the intersection is near, they accelerate. However, when the light turns red, this cues the driver to brake. All right, and this shows 4 possible state transitions in the FOA. In the first diagram, there are 4 active items at time 1, which are marked as white spheres. At time 2, one of these 4 items has been replaced so that one white sphere, B, becomes black, inactive, and a different black sphere, F, becomes white, or active. Thus, 25%, 1 divided by 4, of the items have been updated between time 1 and time 2 without any change in the total number of active items. For clarity, most other figures in this article feature this single item updating. However, in a store with 4 items, updating can occur in 3 other ways. The other diagrams in this figure depict 50%, 75%, and 100%. So just to mention, you guys, this shows the focus of attention in updating in a human mind. I wrote this before ChatGPT was a thing, and the 2016 paper came out before the invention of the transformer architecture for AI. But we see that only having 4 items is a human-like limitation. And chatbots today, or large language models, have context windows that hold, thousands of tokens. Now, those tokens are updated iteratively, but there's no way that so many tokens could create a single scene or event that could be contemplated consciously, right? That's why I think that these systems need to depict smaller groups of concepts and individual events, because I think that that will help the way that they process information. Here is figure 20, 2 rates of updating carried out over 4 time periods. In the first scenario, 71%, 5 divided by 7, updating is carried out over 4 time periods. In the second scenario, 29%, 2 divided by 7 updating is carried out. This comparison delineates the difference between unfocused, minimally overlapping thought, or loose iterative coupling, and highly focused, closely overlapping thought, tight iterative coupling. To better illustrate this point, the capacity of the FOA is depicted here as 7 items after Miller. So instead of 4 here, we're using 7. The Venn diagrams to the right illustrate the percentage of iterative updating in the FOA using the style of figure 13. So I think that here, this first example is basically Kahneman's thinking fast. And the second is Kahneman's thinking slow. So figure 21 shows that dopamine may reduce the rate of iterative updating in working memory. A set of 7 items is held in working memory. That's 57%, and you get that by dividing 4 by 7. 57% updating is carried out over 4 time periods. At T5, the rate of updating is reduced. This might happen when a person encounters a novel set of stimuli that causes the brain to release dopamine and shift from implicit processing, system 1, to explicit attentive processing, system 2. The activity of the items from T5 is sustained, and the concepts are anchored upon, giving them more processing priority so that a greater focus can be brought to bear on them. By time 9, 57% updating resumes. And figure 22 shows intermittent, non-iterative updating marks a boundary between thoughts. So in both diagrams, most of the updating occurs at a rate of 20%. However, the first diagram shows 3 intermittent updates of 80%. The second shows only 1 intermittent update of 80%. This comparison delineates the difference between 4 brief thoughts occurring in quick succession and 2 more prolonged thoughts. The first strategy would result in small islands of associative connections among long-term memory items. The second strategy would result in longer sequences of iterated associations and consequently less fragmented thinking. So I spent more than 20 years developing these concepts and these figures, and I believe that they really show in a unique and novel way the shape of the thinking process. And I think that that can help us understand human thought and consciousness and how the brain works, and then also how to get these systems into a computer for AI. Okay, here's a representation of William James' sliding ruler. This figure is meant to convey William James' ruler analogy, which you can see right up here at the top, for the overlapping units of conscious experience. The ruler encompasses a set of dots. As the ruler slides down a line of equidistant dots, the set it contains is updated iteratively. So I looked for a precedent for this model throughout the literature, and I wasn't able to find one, but I did see that William James touched on some of these concepts over 100 years ago, and he did so in a fun, interesting, and poetic way, and I like the way he put it into words. Okay, so here's part 4, and this are the implications of the model. So here we're seeing concepts of interest at different levels of abstraction. So number 1 is a single neuron. Number 2 is a neural assembly, indicated by a lowercase letter, composed of many nearby local neurons with similar receptive fields. Number 3, this is an assembly, possibly a cortical mini-column, and it's equivalent to a subsymbolic feature. 3 shows a neural ensemble composed of many non-local assemblies. An ensemble is an engram for an item, concept, or mental representation. And then 4 shows 4 ensembles within the focus of attention of working memory. 5 shows items, indicated by uppercase letters, in the focus of attention undergoing an iterative update. All right, and then figure 25 shows 2 successive instances of coactive assemblies in the FOA. The ensembles for items B, C, D, E, and F are each composed of many assemblies of neurons active in association areas, represented by lowercase letters B, C, D, E, and F, respectively. At time 1, assemblies B, C, D, and E are active. At time 2, the assemblies for B have deactivated, while those for F have become active. Thus, time 2 is an iterated update of time 1. And my claim is that this process is happening constantly in the brain. Okay, a semantic web showing associative connections between concepts. 17 concepts or ensembles are represented by circular nodes in a long-term memory network. The existence of an associative connection is indicated by a line, and its strength by the thickness of the line. The 4 items, red, truck, siren, and fire, are currently coactive in this network, and thus spreading activation is likely to select firefighters as the next iterative update. So this shows the multi-associative search algorithm. And I'll let you read that if you're interested. Okay, figure 27, a schematic for multi-associative search. Spreading activity from each of the assemblies, lowercase letters, of the 4 items, uppercase letters, in the FOA, and those are B, C, D, and E, propagates throughout the cortex, represented by the field of assemblies above the items. This activates new assemblies, constituting the newest item F, which will be added to the FOA in the next state. The assemblies that constitute items B, C, D, and E are each individually associated with a very large number of potential items, but as a unique group, they're most closely associated with item F. Okay, and then here, figure 28, is spreading activation weights are redistributed across the sequence. This figure illustrates the process introduced by step 4 of multi-associative search above. Each new addition to the FOA, time t, changes the distribution of activation energy. It spreads more activation energy to certain items in the focus of attention and short-term store than others, shown by the arcs. This differentially increases the item's capacity to contribute to the selection of the next item, indicated by line width below the items. Figure 29, a single cycle of the iterative updating multi-associative search procedure. The FOA, the short-term store, as well as active neurons in the hippocampus, basal ganglia, sensory and motor cortices, all contribute to the spreading activation that will select the next items to be added to working memory. At time 1, 2, G and H, of a potential 5 items are converged on, and these update the FOA in time 2. Figure 30 shows conditional dependencies between consecutive events. Each arc represents the span of time since an event occurred. S represents stimuli, R represents responses, and other capital letters represent items. Figure 31, merging subproblems in working memory. An original problem is activated, M, N, O, and P. The iterative updating is used to reach a solution, O, P, Q, R. This subsolution is saved in the short-term store, and a related subproblem, TUVW, is introduced into the FOA. This subproblem iterates until a second subsolution is generated, UVWX. Relevant items from the first subsolution, Q and R, are combined with those from the second subsolution, W and X, and iterated to generate a final solution, R, X, Y, and Z. And I believe that this pattern could be a fundamental aspect of human reasoning and creativity. Reiterating through an earlier sequence. A set of 6 items held in working memory is iteratively updated over the next 3 time steps, creating a self-contained thought. Starting at T5, attention shifts completely as an unrelated thought takes place using an entirely different set of items. From T9, the first sequence is reiterated as before. This might happen when someone revisits an earlier thought, such as rehashing a plan of action, retracing a set of previous steps, or retelling a story. revisiting the endpoint of an earlier iterative sequence and continuing it. 6 items are modified over the first 3 time steps, creating a line of thought composed of 4 related states. Attention shifts completely at T5, and an unrelated thought occurs. Starting at T9, attention shifts back to the items from T4, which are iterated without using any of the items from T5 through T8. This might happen when someone picks up a thought where it left off and continues to think about the issues from the last point at which they were considered. Okay, and then this is revisiting the midpoint of an earlier iterative sequence and altering it. 6 items are modified over 7 time steps, creating a thought composed of 8 related states. At T9, attention shifts back to a point in the middle of the sequence. This set or subproblem from T4 is then iterated without including any of the items that were introduced from T5 through T8. This creates an alternate branch and a forking of the iterative sequence. This might happen when someone decides to assume an intermediate step in a previous problem-solving sequence and solve the problem in a different way. Masking occurs when 2 independent sequences multitasking occurs. So 2 distinct threads of thought are iterated but never combined, alternating every 3rd time step. This context switching could occur when someone is working on 2 separate tasks or problems simultaneously. Elaborating on a stable subset of items. 3 items are held constant as iteration elaborates on their statistical relationships using related concepts. This process would strengthen the connection between these first 3 items and explore how they're associated with different contexts. Progressing backward to a subset of an earlier state of coactive items. Some lines of thought, by the end, return to the beginning. Here, the first set of coactive items is revisited and re-related to the outcome of the iterative sequence. This circularity could occur when one reconciles a predicted outcome with the original premise. This is probably a common thought pattern and can be contrasted with the previous figure, 36, where the first 3 items never leave coactivity. Okay, linking the beginning of an iterative sequence with the end makes the intermediate steps implicit. 6 items are modified over 9 time steps, creating a line of thought composed of 10 related states. After T10, many states pass as indicated by the ellipsis. Then later, the original 6 items re-enter working memory. Because of Hebbian learning, these items recruit the same 6-item solution reached previously without having to reiterate it. The way probability is modeled has changed due to the earlier iterative work, and multi-associative search is now capable of recruiting the final solution immediately. This is much more likely to happen when iteration involving the first 6 and last 6 items occurs, further entrenching their association. This may happen when one reflects on how their solution reconciles with the original problem state. Okay, employing a previously learned schema. 6 items are modified over 5 time steps, creating a line of thought composed of 6 related states. At time 7, a related schema composed of 11 non-simultaneous items that was learned previously is recalled. This schema, a dynamic packet of information, iterates with items remaining from the ongoing line of thought. This co-iteration results in the utilization of the schema as an organizing heuristic, archetype, or script to guide the thought process. Number 40, figure 40 shows transfer learning. 6 items are modified over 5 time steps, creating a line of thought composed of 6 related states. After T6, many states pass, as indicated by the ellipsis. Then at time 98, an event is encountered that is similar to that at T1, containing half its items. The system recognizes this similarity and incorporates items from the previous line of thought. It thus applies information it has learned to this new context, generalizing, to arrive at a similar conclusory state. Iterative inhibition excludes new items in a search for something more relevant. An original problem is activated in time 1, creating a line of thought that continues until T6. At that point, multi-associative search determines that the most recent update is not a suitable behavioral parameter and it's inhibited. With that item now unavailable, The remaining items continue to spread activation energy that converges on a different item at time 7. The same iterative inhibition occurs for 3 time steps until a suitable item is found and iterative updating resumes. This might happen as someone considers different solutions to a problem. Planning compared to not planning. The first diagram portrays densely iterative processing characteristic of planning. The second diagram portrays 4 mostly unrelated processing states that could not result in a cohesive plan. This comparison highlights the role of intermediate reasoning steps or chain of thought in the planning process. Planning ordinarily involves 1. A lower rate of updating, 2. A lower rate of 100% updates or new unrelated thoughts, and 3. More iterative processing steps before an action is taken. Figure 43, reconciling disparate situations with the same concept. 2 seemingly different situations from T1 and T8 iterate with the same concept, seen twice at T7 and T14. The items at T1 and T8 independently converge towards the idea of T7, T14 as they're reconciled with its fundamental attributes. Perhaps both situations can be explained or caused by the same underlying phenomena and thus are funneled toward this specific region in the conceptual landscape. Figure 44, a hypothetical example of how iterative updating could be found using electrodes. So single cell recording from a large number of cells in association cortex of a person could produce an activity profile exhibiting iterative updating. In this simplified figure, the x-axis represents time in seconds, while the y-axis contains the recorded activity of 30 individual neurons, each remaining active for 4 seconds. 5 neurons become active each second. Each group of 5 neurons that begin and end their period of activity at the same time is assumed to belong to an individual ensemble or item of working memory. And previously we've been seeing these as circles, right, with capital letters in them. Brackets at the bottom of the figure indicate the item to which each group of neurons belongs. This profile coincides precisely with the pattern introduced in Figure 14. Searching new and existing data for this kind of iterative pattern could provide strong support for the present model. Next, we talk about instantiating the model within a computer. So here's a caricature of a language model, a simplified and abstracted representation of a transformer language model. The prompt and ongoing response are kept active in attention along with prioritized aspects of the context, analogous to the focus of attention. Other context is held in the sliding context window, analogous to the short-term store. Symbolic tokens or words active within self-attention pass through the neural network, activating subsymbolic nodes until they converge on the next word predicted from the token output vocabulary. This network progresses from symbolic to subsymbolic to symbolic. Now here's a caricature of a neural network using iterative updating. An abstracted representation of a traditional neural network implementing the iterative updating algorithm. Active sensory input nodes pass activity through the network, activating items within the hidden layers. This activity then passes down toward motor output nodes guiding behavior. But it is the hidden layer representations, not the behavioral outputs, that are routed back through the network cyclically to contribute to determining the next update. This is a naive, vastly reduced implementation of the model proposed here that does not feature a global workspace, modularity, or multimodality. Hierarchical pattern recognition and completion. 3 subsymbolic line segments are detected by early visual cortex. They're at the left. These segments, corresponding to 2 wings and a beak, map onto 3 separate nodes. The nodes each fire at another node higher in the visual processing hierarchy that detects the coactivity or conjunction of all 3. In this case, that node detects the presence of a bird flying in the distance. This is an example of convergent pattern recognition made possible by hierarchical nonlinear transformations. Apparently, the prospect of a bird for dinner enters the focus of attention, creating an impulse to grab a bow and arrow. The neural engram for grabbing becomes active and fires action potentials at motor neurons responsible for the muscular contractions of each of the fingers. This is representative of divergent pattern completion. Essential to sending information to and from working memory in the mammalian brain, convergence and divergence should be emphasized in AI neural networks. A hierarchical artificial neural network structured to integrate information across modules. Each enclosed set of nodes represents a specialized neural network module wired to receive a different input modality. Networks at the bottom left of the hierarchy take input of a single modality from the environment. Other networks take input from multiple neural networks below them in the hierarchy. Spreading network activity would oscillate between the top and bottom of the hierarchy while allowing reentrant feedback or bidirectional signal exchange within and between networks. This figure features 24 networks, each with 19 nodes. An actual build would necessitate dozens of networks, each with millions of nodes. Progressive imagery modification. At time 1, items B, C, D, and E are active in association networks. The spreading activation from these items provides independent yet interactive top-down bias signals to primary visual networks where a composite topographic map is built based on prior experience with these items. This Gestalt sketch will introduce compatible content to working memory. Hence, at time 2, salient features created by the map from time 1 spread activation energy up the hierarchy, converging on the assemblies for item F. Item B becomes inactive while items C, D, E, and F diverge back down the hierarchy toward the primary visual network. The process repeats itself. Because of iterative updating, this process can create a logically connected series of related images. Four examples of working memory activity within the focus of attention. The figure compares the number of items and rate of updating between a human with a limited capacity working memory, a human with a limited attentional store, a typical human, and a superintelligent AI agent. The AI agent can maintain a larger number of nodes over a longer period, ensuring that its perceptions and actions will be informed by a larger amount of recent information. Venn diagrams of working memory in different systems. So we compare a mouse to a monkey to a human to a superintelligent AI. These diagrams depict informational overlap between states of working memory in a span of 10 seconds. The diagrams on the left use the format from figure 13, while those on the right use the format from figure 12. Diagram 1 shows zero overlap between working memory at times 1 and 2. This would make it more difficult for System 1, a hypothetical mouse, to make associations between events separated by a delay. For example, calling this mouse's name and feeding it 10 seconds later may not condition it to come when called, whereas feeding it 2 seconds later might. Training an AI should involve a maturational process where the system begins learning with a minimal working memory span before gradually developing a superhuman capacity for working memory span as formative experiences accumulate. So here are the terms introduced here. Two terms from the 2016 article that I think are interesting and helpful are state-spanning coactivity, which is the sustained coactivity exhibited by a set of two or more items that span two or more consecutive brain states. And then incremental change in state-spanning coactivity, which is the process in which a set of items exhibiting SSC undergoes a change in group membership, where some items remain in SSC and others are deactivated and replaced. So I see SSC there as a different way to conceptualize iterative updating. Here, other models and frameworks that can be integrated with the present model. So these are some other models that I really like, that instead of talking about items, they talk about item-like constructs. So they have different words, operators, symbols, templates, processes. But I think that the model here can be fully integrated with these other models and should be. I think all these models should be integrated with each other. Okay, numerous items orchestrate imagery and behavior in the iterative updating model. Iteratively updated items in working memory interact with sensory cortices to progressively construct mental imagery. They also interact with motor cortices to progressively construct behavior. In the next state, the items in each working memory store will undergo partial replacement. The parameters used in the sensory and motor cortices will reflect this change, making their output an advancement on their previous output. This mirroring of each update will permit them to construct progressive imagery and behavior. Related cognitive processes are included as arrows. The dopamine system, ventral tegmentum, uses inputs from the amygdala and nucleus accumbens to determine which patterns of items match internal incentive templates and thus should be sustained. So here are some of the features of the present model listed in order. And then let me read the rest of this out loud. In his book, The River of Consciousness, Oliver Sacks asks, but how then do our frames, our momentary moments, hold together? How, if there's only transience, do we achieve continuity? This article postulates that our moments overlap in their set of active representations, and that this ongoing confluence results in a flowing progression of states. After asking the question, Sacks quotes William James. Each thought, in James' words, is an owner of the thoughts that went before, and dies owned, transmitting whatever it realized as itself to its own later proprietor. James expounds further on this subject, employing the analogy of a stream. Consciousness, then, does not appear to itself chopped up in bits. Such words as chain or train do not describe it fitly as it presents itself in the first instance. It's nothing jointed, it flows. A river or stream are the metaphors by which it's most naturally described. In talking of it hereafter, let us call it the stream of thought, of consciousness, or of subjective life. As the brain changes are continuous, so do all these consciousnesses melt into each other like dissolving views. Properly, they are but one protracted consciousness, one unbroken stream. That's from 1890. So this is a schematic representation of ongoing iteration in the FOA and short-term memory. This graphic expands on previous figures, incorporating a larger number of the present model's theoretical features. These include the following. 1. The number of items active in the FOA, white spheres, at any point in time varies between 3 and 5. 2. The percentage of updating in the FOA varies between 25% and 100%. 3. The order of entry into the FOA does not determine the order of exit. 4. Items that exit the FOA briefly enter the short-term store as gray spheres before deactivating completely, shown as black spheres. And 5. Items that have exited the FOA are capable of re-entering the FOA. So the present model bears a resemblance to James's conception of a stream of consciousness. A stream is a distribution of points that slides through space and time. Figure 53 extends this activity schematized in this article's other figures over 18 points in time. This results in a depiction of brain activity, working memory, and thought that, shifting gradually, appears very much like a stream. The iterative updating of working memory sustains and shapes the flow of thought. Each new update is an influx of information that acts like a tributary, merging and interacting with the larger current of consciousness, contributing to its rate and direction. Simulating this stream within a computer could play an integral role in enabling an artificial agent to experience a cognitive continuum, traverse the expanse of consciousness, and explore the state space of thought. And then we have the references. So again, I want to encourage you to check out this paper or the sister paper. I also snuck this into my 2012, this just general model, into my 2012 doctoral dissertation. And check out my blog at observedimpulse.com for related info. But once again, you can find this model and all this information at aithought.com.